Alright, this is the third and final video for section 6.3 covering Taylor and Maclaurin series. Question number 7 says to show that the sum n equals 0 to infinity of x to the n over n factorial converges to f of x equals e to the x, and find the interval and radius of convergence. So our function is e to the x, and what we're going to do is we're going to see if we can start developing a pattern of what the Taylor polynomial is going to look like. So f prime of x is e to the x, and e to the x has the easiest derivative to remember. It's itself. The nth derivative of e to the x is e to the x. We're going to center it at 0, so f of 0 is 1, f prime of 0 is equal to 1, the nth derivative evaluated at 0 is equal to 1. So the nth, or in this case I'm going to use k, the kth Taylor polynomial of e to the x is going to be the sum n equals 0 to k of x to the n over n factorial. E to the x is going to be equal to its kth Taylor polynomial minus, plus the remainder. And what we want to do is we want to show that the remainder goes to 0. If we can show that the remainder goes to 0, then e to the x is going, or the Taylor polynomial is going to converge to e to the x. So the remainder is equal to the nth plus 1, a derivative evaluated at c over n plus 1 factorial x minus 0 to the n plus 1. Okay, where c is between x and 0. Okay, so for a fixed x, e to the x is going to be less than some m, and so whatever interval we're on from 0 to x or x to 0, wherever we're at, e to the x is going to be bounded on that interval, and so we can bound it by m, and so we have 0 is less than or equal to the kth remainder in absolute value, which is less than m over n plus 1 factorial x to the n plus 1, and that's going to converge to 0 as x goes to as n goes to infinity. M is a constant, x is fixed, so it's a constant, and n plus 1 is going to explode to infinity, so this limit is going to be 0. And so if our remainder goes to 0, then that means that the Taylor series converges to e to the x here. So e to the x is equal to the sum n equals 0 to infinity of x to the n over n factorial. Now what we're going to do is we're going to find the interval and radius of convergence. So x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial is equal to the limit as n goes to infinity of x to the n times x over n plus 1 times n factorial over x to the n, which is equal to the limit as n goes to infinity of the absolute value of x over n plus 1. Because x is fixed, this is going to be 0. That's less than 1. And so this can be done for any individual x. And so this is going to converge on the entire real number line. And so our interval of convergence is going to be all real numbers. We're going to be able to do some cool stuff with this in section 6.4, where we'll be able to find antiderivatives of functions that don't have an elementary antiderivative, for example, e to the x squared. We're probably going to look at that in the section 6.4. All right, let's go ahead and do one more example of this. So example number 8, we're going to show that the sum n equals 1 to infinity of negative 1 to the n plus 1, x to the n over n converges to the natural log of 1 plus x, and then we're going to find the interval of convergence, and we can also find the radius of convergence. So what we're going to do is we're going to take a couple of derivatives, kind of see if we can get an idea of what the terms of the Taylor series are going to look like. So f of x is the natural log of 1 plus x. F prime of x is equal to 1 over 1 plus x. Second derivative is going to be negative 1 over 1 plus x squared. Third derivative is going to be positive 2 over 1 plus x cubed. Fourth derivative is going to be equal to negative 6 over 1 plus x to the fourth power. And the nth derivative is going to be, let's see what we got going on here. Let's see if we can deduce what this might be. So let's go and evaluate at 0. We're going to center this as 0. So f of 0 is 0. Okay. And I think we got some alternations, so we're going to do a negative 1 to the n maybe. Or maybe a negative 1 to the n plus 1. Okay. So the first term's 0, so we're going to neglect the first term. Okay. So we're going to start here. Okay. And we want that to be positive, so n plus will do that. And then this would be the second term, so 2 plus 1 would be 3, so I give a negative 1 to the third power is negative 1, so that's looking good. Okay. And let's see what we got going on here. This looks like, well, what do we got? This is a 1, and then a minus 1, and then a 2, and then a minus 6. Looks like it's kind of following a factorial of some sorts. So what if we did n minus 1 factorial? So 0 factorial by definition is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and so that is giving us those coefficients right there. That's looking pretty good. Okay. Over 1 plus x to the n. So that's what the nth derivative appears to be looking like. Okay, so let's evaluate the first derivative at 0, and that's 1. The second derivative at 0 is minus 1, and the third derivative at 0 is 2. The fourth derivative at 0 is negative 6, and the nth derivative at 0 is going to be negative 1 to the n plus 1, n minus 1 factorial, over 1 plus 0 to the n, which is just going to be the numerator there. So our nth Taylor polynomial here is going to be the sum k equals 1 to n of negative 1 to the, if we're going to do this, we need to use k plus 1, k minus 1 factorial. Oops, what's happening here? Oh, I'm making marks on the side of the screen there. Okay, let's try again. K minus 1 factorial, x to the k, all over, and that should be a k factorial. Okay, so k minus 1 factorial over k factorial, we can write that as k times k minus 1 factorials, and so those k minus 1 factorials will absorb, and so we're left with just k in the denominator. Okay, so sum k equals 1 to n of negative 1 to the k plus 1, x to the k, oops, all over, oops, go back, all over k. All right, so that is with our nth degree. In this case, it's a Taylor or a Maclaurin polynomial because we're centered at 0. Okay, so let's go ahead and move on. So the natural log of 1 plus x is equal to the sum k equals 1 to n of negative 1 to the, let me fix those k's, those n's there. I'm so used to writing n that it's hard to break habits there. Okay, so natural log of 1 plus x is equal to the sum k equals 1 to n of negative 1 to the k plus 1, x to the k over k. So that's the nth Taylor polynomial, and then plus the remainder, the nth remainder. The remainder is going to be equal to the nth plus 1 derivative evaluated at c over n plus 1 factorial, x minus 0 to the n plus 1. Now we are fixing an x, and so our nth derivative is going to be bounded. So 0 is less than or equal to the nth remainder in absolute value, which is less than or equal to m. So the natural log of x is going to be bounded on some closed interval, so we're okay there. Well, actually, it's not natural log of x. It's going to be some rational function on a bounded set, so it's going to have a min and a max. And so m's the maximum, or just a bound larger than that. So less than or equal to m over n plus 1 factorial x to the n plus 1 in absolute value. And of course, the m and the x, m is a fixed number, x is a fixed number, so it's got a constant, all over n plus 1 factorial, and that's going to outpace the x to the n plus 1, and so that's going to go to 0 as x goes to infinity. And so the natural log of 1 plus x is equal to the sum n equals 1 to infinity of negative 1 to the n plus 1 x to the n all over n. And so let's go find our interval of convergence. So natural log of 1 plus x is equal to the sum n equals 1 to infinity of negative 1 to the n plus 1 x to the n all over n. So we're going to use the ratio test. The limit as n goes to infinity of x to the n plus 1 over n plus 1 divided by x to the n over n. That's going to be equal to the limit as n goes to infinity of x to the n over x. Sorry, x to the n times x over n plus 1 times n over x to the n, which is equal to the limit as n goes to infinity of n over n plus 1 times the absolute value of x, and that's going to converge to the absolute value of x, which is less than 1. So we want the x to be bounded between negative 1 and 1, and so our radius of convergence is going to be 1. Now we want to check to see if we have convergence at the endpoints. So if we try at negative 1, we have the sum n equals 1 to infinity of negative 1 to the n plus 1 times negative 1 to the n. Okay? And that would give us negative 1 to the 2n plus 1, which is always going to be odd, and negative 1 to an odd power will be negative 1. So we'll slide out the negative, and the sum n equals 1 to infinity of 1 over n. And that is the divergent harmonic series. It's a p series, where the p is equal to 1, and that's less than or equal to 1, and that was your condition for divergence. Now let's look at the sum at 1. We have the sum n equals 1 to infinity of negative 1 to the n plus 1, and then times 1 to the n, which is just 1, all over n. And we've looked at this series before, something very similar to it, and this is a convergent alternating series. So you could apply the alternating series test to show that this is convergent. Okay, so then what we have for interval of convergence then is it is going to be from minus 1 to 1. We are not allowed to include minus 1 because it diverges there, but 1 is included. Okay. Alrighty, so stay tuned for 6.4. That's going to be the last section on the chapter 6. We'll see you next time.